Model-based meta-reinforcement learning for flight with suspended payloads. Our goal is to enable a quadcopter with a cable tether and magnetic payload to pick up and transport different ground payloads. Specifically, the quadcopter's task is to control the payload in the image space of an external camera without any motion capture or ground truth state. The control output is the velocity commanded to the quadcopter, and the goal is to have the payload follow the image space target trajectory shown in red. The quadcopter's flight dynamics change when it picks up a payload. Prior methods oftentimes fail because they are unable to adapt online to different payloads. We therefore developed a model-based reinforcement learning algorithm which uses meta-learning to adapt online. At the core of our approach is the standard neural network dynamics model, which takes as input the current state in action and predicts the next state. This model is trained with time series data of length t to optimize the neural network weight parameters theta. Given the payload parameters are unknown, we represent them with a latent variable z, whose distributional parameters are given by phi. During training, we train with k different payload tasks, which enables the model to adapt to different payloads. Our algorithm consists of a training phase and a test phase. In the training phase, we first gather data by manually piloting the quadcopter along random trajectories with a variety of different payloads. We then run meta-training to learn the shared dynamics model parameters theta and the adaptation parameters phi for each payload. At test time, using the learned dynamics model parameters theta star, the robot infers the optimal latent variable phi star online using all of the data from the current task. The dynamics model is then used by a model-based controller to plan and execute actions that follow the desired path. As the robot flies, it continues to store data, infer the optimal latent variable parameters, and perform planning until the task is complete. Here we show our method running at test time. The task is to follow the specified trajectory, shown in red, as closely as possible. The model-based planner evaluates multiple trajectories, shown in white, and selects the best trajectory, shown in blue. As the quadcopter flies, it infers the optimal latent variable. In our experiments, we evaluated our approach on a series of suspended payload control tasks. The following experiments compare our method with a model-based reinforcement learner in which the current state contains a history of the past payload locations and quadcopter actions. In these experiments, the task is to follow the specified trajectory as closely as possible. Our approach achieves a lower tracking error when following a square trajectory. Our approach also achieves a lower tracking error when following a circle trajectory. Here, we show that as our method adapts, it tracks the desired trajectory closer and closer. Our method can successfully control a suspended payload in multiple realistic scenarios. In this scenario, the quadcopter is given a trajectory to follow that avoids the obstacle. By using our method, the quadcopter is able to adapt to the payload and maneuver closely around the obstacle. Adaptation enables the quadcopter to change payloads online. We now show our method performing a full pickup and drop-off sequence. The quadcopter first follows a circle trajectory. Then it picks up the payload and follows a circle trajectory with the payload. Finally, it moves to the target location where a person removes the payload. Then it follows a circle trajectory without the payload. In certain scenarios, like pickup and drop-off, the user may prefer to directly indicate where the payload should go, and let the quadcopter decide how to fly to move the payload towards the desired location. In this experiment, we mounted the camera onto a stick. The robot's goal is to keep the suspended payload in the center of the camera's field of view as the camera moves around. This intuitive wand interface enables the human to direct where the suspended payload should go. Similarly, using the same goal of staying in the center of the camera frame, the human is able to indicate the desired path for the payload in real time while avoiding obstacles. Thank you for watching.